Yeah, I'll just wait for 2 minutes. Okay, because I just.
Yeah, okay, that's fine.
Yeah, I think people are getting tired, so probably we should start. People are not showing up for the morning lectures anymore.
There's always a few people, yeah. I just,
Yeah.
as you said, I'll avoid a picture coming in. But
Yeah,
I
yeah.
think we now have.
Yeah. Okay. Let me review quickly what we have done yesterday. I told you that in conformal field theory, representations are organized according to special lowest weight states, which are primary operators. In models with some U1 symmetry, they would be labeled by scaling dimension, the U1 charge and spin. And then you build up descendants. You build up descendants by just hitting these operators with the momentum operator, or the indices of the momentum operator could be constructed in various ways. And you build up a tower of descendants. And then there is a spectrum of primary operators that we might be interested in. And then we applied the ideas of large quantum numbers to understand how the scaling dimension goes as a function of Q. We just find the lowest lying operator with some given Q, and we argue that that's the scaling law. We even used the theory of small fluctuations of phonons around that superfluid state. We interpreted this operator to be the lowest operator as a superfluid state. At large Q, this interpretation makes sense. And then we looked at the phonon excitations on top of that superfluid. And we argued that the gap to the next primary should scale like that, with the proviso that the spin 1 phonon is actually a descendant. So the other phonons create new primaries. And this leads to a curve that looks like that, where the scaling dimension is measured as a function of charge. Roughly, it's some Q to the 3/2. And the phonon theory allows you to predict the next couple of primaries and their descendants. And of course, at some point, this effective field theory breaks down, because the cutoff of this effective field theory is roughly when the gaps become of order Q to the of order square root of Q. So you can trust this up to some point, but you cannot go beyond that. So one thing I forgot to mention yesterday is up to which point can you trust this? And the answer is that you can trust it basically up to J, which scales like square root of Q. Because square root of Q is just the cutoff of the theory. So you can capture a few of the primaries, but of course, at some point, you cannot capture anymore. And we believe that like these highly excited primaries would be chaotic and like generic thermal states, and we won't be able to discern them or say something intelligent about them beyond statistically. Okay, beyond statistics. Are there any questions about the review of yesterday? Before I move to the new topic and my last topic. So the new topic is we will try to understand what are spinning operators. So highly spinning primary operators, not descendants. Highly spinning descendants is trivial. We just hit the primary with lots of derivatives and we get a highly spinning descendant. Today we'll try to understand highly spinning primaries. And so my strategy is that I'll first quote the result. I'll show you that the result can be reproduced by assuming some form of ADS-CFT correspondence. That ADS-CFT correspondence is not like fundamental. It's just a way to capture the large spin primaries. And it allows you to do computations with very impressive precision. But it's not a true holographic duality. It's just capturing correctly the large spin limit to all orders in the 1/spin expansion. One thing I will not do, I will not prove that this is the correct universal result in the large spin limit for any theory. I'll just quote the result and show you how to do computations in ADS. I will not explain why this is the correct result for any known or any theory. But people have proven that this is the correct result. I just cannot review the proof here. It's too convoluted, and it's referenced in the notes. So I decided to just show you the result and how this comes about from the ADS CFT, but I'm not going to prove that it holds even in models which are non-holographic. So the result is the following. If you take any primary operator, let's call it O1, and you take another primary operator, O2, of course, this goes without saying, nobody guarantees that the product is a primary operator with scaling dimension delta 1 plus delta 2. It doesn't work like that because there is operator renormalization. There might not even be an operator like O1 times O2, and it might have a completely different scaling dimension than what you might conceive. For instance, in the Ising model, we have a spin operator, sigma, the spin field that I think Clay encountered in his lectures. In 2 dimensions, its scaling dimension is 1/8, but if you take the product of 2, the scaling dimension is 1. Okay, so there doesn't have to be a good notion of what do you even mean by O1 times O2. But the central claim of the large spin limit is that if you, between these 2 operators, sprinkle Laplacians n times and derivatives j times, so these derivatives are symmetrized. So here the indices of the derivatives are constructed to get a Laplacian n times, and here the indices of the derivatives are in a symmetric traceless representation, j times. So the claim is that if j is large enough, and n, let's say, is order 1, could be 5, 7, this is a primary, and we can compute its scaling dimension as if it was a free field theory. So the result is that these objects, so the first point is that these objects exist, they're primaries. You have to construct the derivatives carefully. I'll show you later. So the derivatives have to be ordered in a very careful way to get an actual primary. So it's a linear superposition of many, many ways of distributing the derivatives. I'll show you the explicit formula in a half an hour. But there is a way to distribute the derivatives that you get the honest-to-God primary. So claim number 1 is that such primaries actually exist. Such primaries exist. There is a shorthand notation for these primaries in the literature. We denote these primaries O1, O2 in square brackets indexed by n and j. That's the notation that commonly appears in the literature. So first of all, we claim that these primaries exist. And secondly, we claim that their scaling dimensions are computed as if it was a free field theory, even if the underlying conformal field theory is strongly interacting. And it's true for any O1 and O2. Okay, so the scaling dimension is claimed to be just the sum of O1 and O2. You add the dimensions as if it was a free field theory. And then you add 2n for these 2n derivatives. And then you add j for the symmetric representation here. And this primary, obviously, what are the quantum numbers of these primaries? They have spin j. That's why I call it j, because this is a traceless symmetric representation of spin j. And this little n doesn't change the quantum numbers. It just adds a little bit of scaling dimension. If you want to get the true lowest spinning primary, you just put n equals to 0. And okay? So the claim is that they exist. These are their scaling dimensions. And the corrections to this formula, it cannot be exactly free, of course. There are corrections to this formula, and the claim is that these corrections go like 1/j in 3 dimensions, and 1/j squared in 4 dimensions. So I'll just put d minus 2. The claim is that these corrections go like 1/j to the power d minus 2, with some coefficients that we will compute today in some approximation, but they are known exactly. And also, this whole business fails in 2 dimensions. So if you're an expert on 2-dimensional conformal field theories, like those that appear on the worldsheet in string theory, you have never seen those primaries. They don't exist in the Ising model, for instance, because this formula fails in 2 dimensions. And these corrections are large, and there is no such thing in 2 dimensions. These people have developed this theory of high spin in 2 dimensions separately. You can look at the work of Shridi Pal, for instance, and many others. But I'm going to talk about higher dimensional conformal field theories to avoid this nuisance. Yeah.
It seems like in 2 dimensions, the corrections would still be order 1, so maybe delta equals j would still be somewhat meaningful?
That's a good question, but even that doesn't hold. Yeah, even that is not true, it turns out. So the question is, can you trust maybe this piece in 2 dimensions? And the answer is kind of yes and no. So what people have shown is that you can kind of trust it, but the picture that you get for which primaries exist is more complicated. I really don't want to get into it. Some people, such as Sridip and where's Siwai? What's the name of the person from IHS that wrote many papers about it? Jiaxin. So there are people that dedicated many years to figuring it out. And so I don't want to get to d equals 2. Okay, so this is the claim that they exist. There are small corrections. And today I'll show you how to capture it, how to compute these corrections. So one thing is that I think just to make it sound a little bit familiar, I'll just say that this is like asymptotic freedom, right? What was the statement of the asymptotic freedom discovery in the 70s? The statement was that at short distances there is weak coupling. Here we see something new, that in every CFT, even if it's extremely strongly interacting, like the Ising model or O2 model or some gauge theories in the conformal window, we have a parton picture. It seems like these are some kind of partons, like particles. And then this seems like a classical dispersion relation. And there are small corrections due to weak interactions. So it seems like you have some kind of asymptotic freedom, but it's not at short distances. It's large angular momentum. So there is a picture of partons that appears in every strongly interacting theory. And the effective coupling, you can call it H bar effective, goes like 1 over the spin, okay, to the power d minus 2. So somehow you get weak coupling in arbitrary conformal field theory. Is the existence of these primaries verified by Monte Carlo or the bootstrap? Yes. I attached in my notes that I put on Slack 2 plots from bootstrap and Monte Carlo simulations. And you see the following thing. This is in 3D XY model, the model that I spent quite a bit of time explaining to you. So people have plotted delta minus J versus J, and let's say 1, 2, 3. And the picture that you see is that it's like that. It becomes flat, exactly like the formula predicts. And if you continue this line here, you get 1.02. Okay, so you get 1.02, and that's exactly what the formula predicts, because if you plug little n equals to 0, then you find that delta minus J is the sum of the scaling dimensions of the partons, but the scaling dimension of the parton in the XY model, as we reviewed in the second lecture, is 0.51. And it works beautifully. Another thing is that it approaches from below. And today I'll compute this correction for you in some cheeky way. And it turns out to be negative. So it also matches the qualitative feature of the Monte Carlo or bootstrap results. Okay, so I'll show you where this asymptotic freedom comes from today and how to compute these corrections. Are there any questions about, because, okay, so from now on, I'll just teach you how to see this in ADS and how to compute these corrections from ADS. I will not explain how to prove that this is true in every field theory again, as I said. So are there any questions about the statement of the result? Okay, good. So we have asymptotic freedom, partons, small h bar. And now I'll switch to explaining some very basic stuff about particles in ADS D+1. It would seem completely disconnected, but at the end you'll get, it's a machine to calculate. It's a machine to calculate in this asymptotically free regime. So in QCD, people realize that there is asymptotic freedom, but then there is the parton picture on top of that. So there is some calculational scheme of how to do calculations at short distances. So for me, ADS D+1 will be like a picture where the partons come alive, and you can do calculations. So it's just a calculational scheme. Even though it looks remarkably like the ADS CFT correspondence, it's just a calculational scheme where the partons become actual particles. Okay? So that's the reason that ADS appears in this discussion. So what is ADS D+1? I assume you'll see it in other lectures. But it's defined as a hyperboloid obeying this constraint. And L is the radius of ADS. It's just a hyperboloid embedded in R 2, D. It's a hyperboloid in that. And then I'll choose particular coordinates today where x-1 and x0 are given by L, sec, rho, and then sine. Oh, sorry, that was cosine. Cosine T, L, sec, rho, sine T. And then xi would be L, tan, rho, omega I, where omega I parameterize a d-1 dimensional sphere. So this goes from 1 to d. Okay, these are the coordinates that I'll choose. In those coordinates, you get the metric of ADS D+1. There is an L squared out front. And then there is 1 over cosine squared of rho. Then there is minus dt squared plus d rho squared plus rho plus sine squared rho d omega squared. This is the metric on the d-1 dimensional sphere. So I'll just put d-1 here. So this is the metric. Let me just draw a picture. So it's like a cylinder. You should think about ADS D+1 as a cylinder. Time runs up, and this is the this is the d-dimensional space-like slice. And the rho coordinate is measured from the origin to infinity. So rho goes from 0. And here at the boundary, rho is pi over 2. But the geodesic distance is, of course, infinite, because you see cosine squared blows up at rho over 2. OK. And there is time. OK, now ADS D+1 is convenient as far as the isometries go, because ordinary isometries in ADS D+1 are the same as the conformal isometries in conformal field theory in d dimensions. So the ordinary isometries, not the conformal, just the ordinary isometries of ADS D+1, they furnish the same group as the conformal symmetry in in CFTD. So that's SOD2. So that's the same as the conformal group. That's the same as the conformal group of R D-1, 1. Okay. And so we have to match the symmetries to understand how this representation theory is going to work. So what are the symmetries of this hyperboloid? That's kind of trivial because it's just like a sphere. So the symmetries come from rotations of the hyperboloid. So you have all the symmetries of the hyperboloid are just the JAB, which is given by XA dB minus XB dA, running where A and B run from 0 to from -1, 0 all the way to D. And so let's identify quickly what are the symmetries. So J minus 1, 0 is time translations in ADS. That's time translation in ADS D plus 1. Importantly, that is through this correspondence with conformal isometries of RD minus 1, 1, that's the same as dilatations or dilations. And therefore, there is a correspondence between the energy in ADS. It's just a representation theory correspondence. It's not something deep yet. So the energy in ADS D plus 1 is the same as the scaling dimension in conformal field theory. So you get a nice formula that the energy in ADS D plus 1, if you multiply it by the radius of ADS, you get the scaling dimension in the conformal field theory in D dimensions. That's the correspondence. Then the J, I, J are just rotations. And J minus 1 I, as well as J 0 I, they correspond to P and K. And what were the P and K in conformal field theory? They were the raising and lowering operators of the descendants. They act as ladder operators on the descendants. Okay. So if you want to do a small exercise for your education, you can try to figure out which linear combination is P, which linear combination is K. That's just coming from the commutation relations with the dilations, because one is raising, one is lowering. So it's a small exercise for you to do if you want. Now there is a Klein-Gordon equation in ADS. Let's say we have a free field in ADS. This is the Laplacian in ADS D plus 1. There is a Klein-Gordon equation. We can try to solve it and have fun solving it. You can also think about the Laplacian as the Casimir operator of the isometries, but that's like for every homogeneous space. The Klein-Gordon operator is just the sum over the generator squared. And the first thing I want to do is just to tell you what wave functions appear, making some contact with the representations of conformal field theory. It's just a little warm-up kinematics. So there are many wave functions, and we have the same structure as for operators, primary operators in conformal field theory, because we have raising and lowering operators. So it's very important that P raises the operator, P raises the energy of a wave function in ADS, and K lowers the energy of a wave function in ADS, because they satisfy the same algebra as conformal field theory. So therefore, if you think about wave functions in the cylinder, some particles in the cylinder, there is raising and lowering operators. So what does intuitively P do? If you have a wave function of a particle that's like at the center of ADS, maybe some wave function of a particle that's pretty stationary at the center of ADS, what P is gonna do is to make it spin. And K is gonna bring it closer to the center if it's possible. So if you look at any wave function, it sits in the same representation. It sits in a representation which is lowest weight state. Because you act with P, it makes it spin around the center of ADS. Remember that ADS is like ADS is a little bit like some kind of trap. You can think about ADS as some kind of gravitational well with gravitational potential that goes like distance squared. So if you like classical physics, you can think about ADS as a source of gravitational potential that goes like the distance squared. Well, sorry, not in these coordinates. In these coordinates, it's going to be exponential. I think it's 2 rho. So you can think about ADS as an exponential gravitational well. So particles can sit at the center at equilibrium, at gravitational equilibrium, or they can spin around the center if you give them angular momentum. So a special set of wave functions are the primary wave functions. These are the wave functions that if you act on them with the differential operator k, they would annihilate those wave functions. Those wave functions are expected to be at the center of ADS, and then you can spin them around by acting with p. So you can write an explicit expression for k using the coordinates on that board. So I'll just spare it and write it for you. So essentially the differential equation that you get, assuming that the wave function, well, you have to make an assumption about what is this wave, which particle are we looking at? And I'm going to assume that it's a scalar particle. So you could discuss gravitons in ADS, you could discuss spin-3 particles in ADS. Let's just do a scalar particle. That corresponds to a scalar primary operator. So it's the same representation theory as a scalar primary operator. So for scalar wave functions psi, the expression for k is sine rho dt plus I cosine rho d rho. So you just need to solve the differential equation that this annihilates a wave function. And from that, you get a very simple wave function. I'll just write it here. You get e to the minus I delta t cosine delta of rho. So that's what does this wave function describe? Well, there is the usual time oscillations because it's an energy state. And the energy of the state in ADS is delta. And I promised you that it's, well, I have to put L. I'm sorry. I accidentally put L equals 1. For dimensional analysis, there must be an L here. So it has to be T. Let me check that that's what I'm saying is correct. So T is no, that's okay. T is dimensionless in my conventions. So the energy in ADS is going to be L delta. Yeah, okay. So that's actually correct. Sorry. So we have a wave function. What does it describe? It's a wave function that quickly decays near the boundary because the boundary is at rho equals pi over 2. So it's just a quickly decaying wave function, exactly like I tried to show in the figure. And it has energy delta. And you can ask, what Klein-Gordon equation does it solve? Because we just solved the lowest weight condition. The Klein-Gordon equation would allow you to compute the mass squared. And guess what? You get the formula that you've seen in the ADS-CFT correspondence. That's the connection between the mass squared and the energy in ADS, which is the scaling dimension. That's, of course, a formula that you may have seen in a basic course on the ADS-CFT correspondence. Okay, so we have these wave functions. And now, if we like, we can just spin them. We can act on this wave function with the differential operator p and make them spin around the center of ADS. I don't really need to write explicitly the full wave function and the normalization. It's in the notes. I'll just write approximately what the wave function looks like. So it's a wave function with spin j. This is the Casimir of the rotations. And let's say component jz along some axis z. Let's say in well, I'm thinking about ADS 4 here. So, okay. Sorry, I'm thinking about, yeah, I don't need jz actually. That would be for ADS 5. For ADS 4, we don't need jz, so we just have that. So we have some normalization factor that I'm not going to write. We have some energy that I'll compute in a second. Then we have some spherical harmonic, which is in ADS 4, it's very trivial. It's just the ordinary spherical harmonics. Oh yeah, I'm doing ADS 4, so I do need jz, I'm sorry. So it's just the ordinary spherical harmonic, which depends on j and jz. It's a function of theta and phi. And then finally, you see the fact that this particle is now spinning because you have a sine of rho to the power j and a cosine of rho to the power delta. So now the wave function doesn't decay that quickly, right? Because the sine function has big support near the boundary. So the center of the wave function has shifted from rho equals to 0 to some non-zero rho. And you can just calculate approximately where this wave function is peaked. And you'll find that rho star satisfies the tangent squared of rho star, where this wave function is peaked, is j over delta. Okay? It's just a particle swirling around ADS. And it will be important for me to calculate the geodesic distance. I want to calculate the geodesic distance to the center of the rotation of this particle. Just 1 second, I'll write the formula for the geodesic distance. So to calculate the geodesic distance, we need to integrate from 0 to rho star of the metric. We just integrate the line element. We just integrate the line element from rho to rho star, and we get that it's the radius of ADS by 2, and then logarithm of 2j over delta. Just remember that formula. It will be very, very important. Yeah. T is so yeah, you see in my conventions here, yeah. T is dimensionless, and therefore the exponent is dimensionless, and I'm good.
But for the psi j1, j2, you wrote the exponent as e times t?
Yeah, but I haven't told you what E is yet.
Okay. So
E is, in these conventions, Ej is delta plus j. And why is that? That's what we've seen with descendants. What is this wave function? It's similar to a descendant which you obtained by acting with j derivatives. So you just raise the energy by j. Okay?
but you arrived at this by acting by some p.
P. Yeah, just act with this. Yeah, you get this wave function by starting from the primary wave function and hitting it with P. That just makes the particle swirl around. Okay, it's a descendant wave function. Why am I doing all of this? You might ask. Actually, this is the most important formula, just to remember the connection between the spin and how far it's spinning from the center of ADS. So next is maybe some non-trivial small jump. So I'll make a non-trivial jump now. Suppose there are two particles in ADS, and suppose there are no interactions. Just free fields in ADS, no interactions, and we look at two particle states. There might be primaries. There might be primary wave functions which are made out of two particles, right? Yes, Ben.
Is there an absolute value in this log, or is there some significance to j being less than delta?
Sorry, so you're asking, yeah, this formula is in approximation.
Okay.
You see the squiggly signs? That's valid when j much bigger than delta.
Okay.
Just very large spin. Otherwise, you have to do this integral exactly. And what do you get? Maybe arc tangents of cosine or something. So there will be a more complicated formula. Yeah.
Quick question. So back when we were solving for the original wave function of just the k psi equals 0, how did the deltas pop out in that calculation?
Oh, so the question is, how did the delta appear? So all I did is to solve for a wave function in ADS. I didn't say what is delta. And the solution looked like something that oscillates. You can call it m, whatever, times cosine. But then I said we have a dictionary between representations in CFT and representations in ADS. And I know that the energy in ADS is the scaling dimension in that putative boundary description. So I just, to save notation, I just called it delta, because we can identify it with the scaling dimension of some putative primary. As far as the lowest weight representations go, just think about delta as the lowest weight, the Cartan under the energy, the dilatation eigenvalue of the lowest weight representation. So it's just a representation theory identification. It's not something deep. Yeah? Was there any? Okay. Okay, so now the key next thing is that it's also allowed to consider two particle states in ADS. That's also allowed. So we have this gravitational well, and we can consider two particles. And in free field theory, any product of wave functions is a good eigenstate, right? So we might consider some wave function with jz and multiply it by the wave function of some other particle with some j prime jz prime. This would be a good eigenstate because it's a linear theory. It's just a state in the Fock space of a particle in ADS. Would it be a primary? Probably not. To construct primaries, we need to start summing over maybe j, jz, j prime, jz prime, and we may need to put some coefficients. J prime, jz prime, jz. So it's actually kind of difficult to construct primaries. You need to make some complicated linear combinations. How do you find them? You have to apply the operator k. So you have to look for vanishing solutions under k acting on this thing. Yes?
The operator k is a differential operator that's going to have piecewise on the first one and on the second one. So if it kills the first one, it shouldn't matter that it's in a product. I don't see why just taking the product.
Excellent question. So Yankee is asking why, if this one is a primary, then why is the product primary? Does anybody want to respond? What was the wave function of the primary? Try to remember. What was the primary wave function for one particle state? No, but it was the one that sits at the center. The ones that are swirling around are not primaries. I'm now trying to concatenate a primary from products of wave functions of swirling particles. Okay? It's kind of difficult, but there are wave functions like that. And I'm going to tell you intuitively how they look like. So they look like a particle that's spinning in ADS, let's say anti-clockwise, and a particle that's chasing it exactly antipodally. Oh, sorry, maybe it's a terrible picture. How I want to draw a particle that's chasing it antipodally. Yeah, I'll try to draw it nicely. Sorry, and then maybe I'll draw. Maybe, I don't know. Can you do you see what I'm? No. It's going. No way. How do I make it go up? Sorry, I'm so bad at this. Maybe. Yeah, they just go up. It's like a helix. And they are antipodal to each other. So I claim that there is a wave function that's a terrible superposition. It's a very complicated superposition. I actually calculated it for you in the notes. It has gamma functions, and it's difficult exercise. But it's a nice exercise if you want to play with this kind of problem. There is a wave function that mirrors this intuition. Two antipodal particles. DNA, yeah. Yes. Maybe there is a duality.
Lerman and Reeve, 2005. It was called DNA. It came out of
Okay, I claim that there is a very special two-particle primary that's made of descendants, products. So each individual wave function is a descendant, but you can arrange that this would be a primary, and they describes the figure is that it describes two antipodal particles chasing each other. And antipodal is important because even if you add small interactions, the state would be stable. So it remains a primary, even if you add interactions. So we kind of shut off interactions for now, but imagine that there is a small gravitational interaction just because of Newton's law. Particles attract each other. Or maybe Coulomb's law, maybe they're charged. So if they're antipodal, it's a very nice arrangement because then it will be an almost exact wave function, even including interactions. You would have to fix it a little bit because they might come closer or maybe drift a little bit apart, but it would be almost a good wave function even in the presence of interactions because they're antipodal. So they can, if they were not antipodal, they might merge. But if they're antipodal, there is no way for them to merge. So all the gravitational interaction would do is to bring the trajectories a little bit closer to the center, or a little bit further away if it's Coulomb repulsion. But they're not going to be able to. But that wave function would not become like a resonance. It would not decay, because there is nowhere for it to decay by the antipodal because of the antipodal kinematics. Yeah.
Just for the intuition, I might expect to get a primary for the two particles to spin in the opposite directions.
So the question is, would you be expecting to get a primary if they were to spin in the opposite directions?
Yeah.
I think no. Maybe for large impact factor, but for these are great questions, because I think whatever you find in this kind of domain would have some ramifications for conformal field theory. But my intuition is that it will be more difficult, because if they spin in the opposite direction, then they come close to each other at some point. And suppose they had gravitational interaction, they might form a black hole. It would not be a really good eigenstate. Maybe if they have a very large impact parameter, then it will be okay. But then there will be some phase shift that you acquire. I don't know. These questions I'm not dismissing it, because I think it's a legitimate question and it might have some ramifications for, let's say, but this would have zero angular momentum. The point of the thing that I'm telling you about is that they're spinning in the same direction. So the total angular momentum is J. And I'm claiming that this is like the ground state at some large J. I will claim that. While in your configuration, it would be some interesting primary at zero spin, but it would be what people call sometimes a scar. So I think what you described is kind of in the literature. People have found that there are these special primaries that have a very long lifetime because they have a large impact parameter, and they're called the scar.
Oh,
It's like a generic. It's kind of a special periodic state or pseudo-periodic state in a chaotic system. It has no interest in quantum numbers. So there are papers about it from various people. It's like a scar in ADS. But what I'm describing is not a scar. It's the ground state at some large angular momentum. It's the first primary at some fixed J. And it's not a scar in that sense. It's a ground state. Yeah. But yeah, there is a lot of papers about this kind of scars, like the kind of things you mentioned. Any questions about it? OK, so because such a primary exists, and because I'm assuming that we don't have any interactions now, we can just compute the scaling dimension. The scaling dimension is the energy in ADS, OK? It's the same thing. We can compute the scaling dimension to be the sum of the rest energy of the partons plus the total spin plus, OK, possibly there, possibly there's another integer here that you could introduce. Its physical meaning is that these particles would like be a little bit fatter. There are wave functions labeled by some integer here that are primaries. This integer appeared when I told you what the result is. For now, I'm not going to put it in, just because this is simpler. So this is the leading order result for the energy in ADS. And then there are some small corrections because of interactions. There is always some gravitational interaction, et cetera, et cetera. OK? And now the claim is that while I'm doing some stupid exercise for free fields in ADS, that actually describes conformal field theory, any conformal field theory on the boundary. And the question is, why the heck? Yeah? Because these generic conformal field theories are non-holographic. They don't have an ADS dual. So why would these states exist? So the philosophy is that what is so special about the ADS-CFT correspondence? The thing that makes the ADS-CFT correspondence interesting and non-tautological is the fact that there is local gravitational physics in the bulk. So we can write Einstein equations, and we can trust it even on small scales that go below the cosmological scale, L. So I think the ADS-CFT correspondence is non-tautological only because you can trust the Einstein gravity in the bulk on distances much smaller than capital L. Is that clear? So that's called sometimes sub-horizon locality or sub-cosmological locality. So what I'm trying to say is that If there was no locality in the bulk, in the ADS-CFT correspondence, then it would be a tautological statement because the symmetries match. So there is always something that you can put in that would reproduce what you want. So the non-trivial content is in the locality. But here, this is where this formula becomes important. Here, when the spin is large enough, the geodesic distance is far more the cosmological scale L. So the claim is that even if there is no local ADS theory, let's say for the O2 model or the 3D Ising model, there is no holographic description. But because the distances here are super cosmological, much bigger than the curvature scale of ADS, ADS-CFT works. Okay, that's essentially the point. Because this rotating trajectories, if J is very big, very big, let's say bigger than delta, bigger than 1, if these trajectories are very fast spinning, they drift very far from the scale L. And you can just say ADS-CFT has to work because of kinematics. Because it's just contentless almost. There is no local gravitational physics. Okay, so this is the philosophy. It's not a proof, but this is the idea of why it should work. So the idea is that somehow a piece of the ADS-CFT correspondence holds in every field theory when you go to super cosmological scales.
Yeah, but this is just kinematics, that matching symmetries.
Sorry. So the question is whether this is kinematics. I don't agree with that because this predicts that there are primaries with these scaling dimensions. So the result is highly non-trivial. It means that there is no operator scaling dimensional renormalization for operators with large spin, that they behave like they are partons.
Yeah, maybe can we, like what equation do we solve to get that delta for this composite primary?
We try to find the primary. So we try to impose that this special linear combination is a primary state. So you impose the differential operator K on this, and you solve it, and there is a solution. And we claim that that primary in ADS actually mirrors a primary in the full non-perturbative, strongly coupled dual field theory.
But how is that delta on the left-hand side defined? Right, you would substitute K acting on that composite primary?
That's the energy of this state. Because you find some two-particle state in ADS D plus 1, and you ask, what is the energy of this state? And to leading order, if you neglect ADS D plus 1 interactions, it's the sum of the energies of the underlying one-particle states. And each one contributes, as we said, its mass plus its spin. Maybe I should say J double prime here. So the J double prime plus J prime is like J. So we make up the total spin from the two spinning particles. Let's say, in the notes I showed that the leading contribution is when the two spin approximately, the two partons carry approximately a half of the spin. So that's kind of obvious that this would come out, but yeah, you have to show it. Okay? So it's highly non-obvious that this is true, and it's very difficult to prove. But this machine gives you a way to understand what are we talking about. Why are these primaries there? There is also another idea that goes back, I think, to Giorgio Parisi, who suggested some years ago that perhaps when you put so many derivatives, you remember that the construction in field theory was that we have a composite operator, and then we sprinkle lots of derivatives here. So Giorgio had some idea that he told us a few years ago that perhaps when you sprinkle so many derivatives, it's like you're separating them in space. Okay? And that's why there is no composite operator in normalization. So it's kind of maybe a similar intuition to that. Okay. Yeah.
So would you say that if I handed you an arbitrary CFT and we only cared about constructing into the bulk some theory just in the vicinity of the boundary, you could systematically construct a non-local theory in the bulk that would reproduce the CFT?
Okay, the question is, can we systematically construct a bulk theory that would reproduce the CFT?
If you don't care about locality.
If I don't care about locality, then I think the answer is tautologically yes, in my opinion. At least to all orders in the 1 over J expansion. I don't know if non-perturbatively, but to all orders in the 1 over J expansion, I think it's fair to say that yes. And I think Wei Li, where's Wei Li? He has a paper that does that to pretty high orders. No? No? And I think there is great evidence that you can really systematically go order by order. And now he's already looking at some pretty high order corrections in ADS with some contact interactions, and it still works. So I think the belief in the community is yes. Order by order, you can just tautologically reproduce the answer. Okay. And well, as I said, the proof is in the pudding. It also reproduces the bootstrap results. I mean, you can see that this is happening in non-perturbative strongly coupled theories. Okay, last thing is I want to show you how to calculate small corrections. I'll only do one. So these are antipodally rotating particles. And the only small correction that I'll try to calculate is the fact that they have a gravitational force. Small G Newton suppressed gravitational force. And that should lower the energy a tiny bit. Why? Because it's the gravitational force. So they sit in a gravitational well. So I'll just show you the calculation of how it goes. The gravitational potential in ADS is given by, well, there are some funny coefficients you can see in the notes. You just solve the Poisson equation in ADS. So you get some formula very similar to Newton's law, but unlike Newton's law, the gravitational force does not decay as a power law with the geodesic distance. It decays exponentially with the geodesic distance. That's just a fact about ADS, because ADS is like a box, so there is no massless graviton. In ADS, the graviton is kind of massive, and that's why you have exponential decay of the gravitational force between two particles. So all I need to do is to leading order in G Newton, I just have to calculate the geodesic distance between these particles, shove it into that formula, and that will give me the leading order correction to the energy of the state. And that's why I put this formula in a framed box here. That's the geodesic distance of a single rotating particle around the center. We have now two of them, but each one carries a half of the spin. So I just need to put the geodesic distance from the first particle to the center, where j is replaced by j over 2, and then add another factor of 2d. And after the dust settles, you get a minus 4 G Newton over 3 pi m1, m2, and then 1 over j. Okay? And now we can convert the masses of the particles in ADS to the scaling dimension. How? Because we have the formula mass squared is equal to delta minus d. I'm just going to approximate this formula by saying that mass is like delta to leading order. So we get something like, oh, why is there a square? Sorry. Mass is like delta. Yeah. So I get something like delta 1, delta 2, 1 over j, up to some numerical factors that you can find in the notes, with a negative sign, crucially. So roughly speaking, we now have the first correction to this formula. So the first correction is delta O1 times delta O2 divided by j. And an important, what do you do with G Newton? Because there is no such thing as G Newton on the field theory. Yes?
Why is it 1 over j and not like delta over 2j?
Yeah, I made a small mess. I hope nobody would catch it, but I accidentally put the formula for the gravitational force in ADS5 rather than ADS4. In ADS5, the gravitational force decays like twice the geodesic distance. In ADS4, it's actually like that. So I made a small mess. I have to just tell you what to do with the gravitational constant G Newton. So I'll do that quickly, maybe just slightly for slightly more advanced students. I have to translate the gravitational constant to something measurable on the CFT to write a formula in terms of CFT data. And there is something that's called a central charge in the CFT. And there is a linear relationship between the central charge and the gravitational constant, which goes like the central charge goes like inverse gravitational constant. But there are some pi's and 3's in this formula. So that's why when it's a small kinematic exercise. When the dust settles, there is a central charge in the denominator. And that's it. And then you can ask, is it exact? Is it correct? Is it exact? Okay, this is the last 5 minutes. I'm just going to make comments about this. You can, of course, go to higher orders. So what did I do? I used the gravitational force between point particles, which is a Newtonian approximation, to calculate how much energy is saved by the gravitational force, or how much energy is by how much the energy drops due to the gravitational force. This was a classical computation of two particles rotating antipodally. It's not exactly correct, because what's the true state? The true state is this complicated superposition of wave functions with some complicated gamma functions. And what you really have to do is to do first order perturbation theory in quantum mechanics. Plug this exact superposition of two particle states into the Hamiltonian and ask what is the first order perturbation theory with the gravitational force. And you don't use the Newton formula, because the Newton formula is valid for point particles. And these are not point particles. These wave functions have some little width. So the true formula is far more complicated. It has some gamma functions of delta, and it's a very nasty formula. I put it in the notes on Slack. But this quick and dirty computation reproduces the exactly correct answer when delta is much bigger than 1. Because when delta is 10, let's say, the particles have a very narrow wave function, because the width of the wave function is 1 over square root of delta. So this reproduces the correct answer in the large delta limit, and J is even bigger. So you need to assume that delta is kind of big, and J is even bigger. But if you don't want to make those assumptions, there is the full formula in the Slack note that I published with all the gamma functions. And it's that full formula that comes from evaluating the gravitational interaction of this complicated superposition that we compare to data. Because when we look at the spectrum of the 3D Ising model or O2 model, we have this piece of the curve, and we see that it's approaching the asymptote with ever decreasing gap. And then we compare this prediction with all the gamma functions to that, and it works perfectly. Okay? So the gravitational interaction among two particle states in ADS d+1 exactly captures the correct deviation of the partons from being free fields in the conformal field theory. And that has been shown with great precision. More recently, people like Whaley and others are considering more complicated rotating configurations of many particles. They have, let's say, 17 particles. They try to find the ground state, and there are some molecules. It's a very rich story. But this is the basic example, what I showed you now today. OK? So maybe I'll leave 10 minutes for questions about anything that we covered in this course. This finishes what I wanted to say today. OK, yeah.
What's the relation between this ADS derivation and the superfluid things that we were doing the other day?
OK, the question is, what's the relation between, what's the relation between this and the previous lectures? So both are large quantum number questions about conformal field theory. You can also ask a more concrete question. Can I also put large J and large Q and try to see if I match with the Q to the 3/2 law? And people are trying to do that. So that's why people are studying configurations of many particles rotating in ADS, because that way you sprinkle some Q into the system, and you have large J, and you try to understand where is it going, to try to match the two descriptions. There should be some phase diagram as a function of J and Q.
I guess I meant more like we had some potential for higher angular momentum in the original CFT to arrive at a similar superfluid description without going to the 3DS.
Right. So the question is, so what I described are the ground states of this Hamiltonian. Let's say when the rotation speed is the speed of light. So I described to you these double twist operators that are made from these rotating particles. They're the ground states of this Hamiltonian. Sorry, it's not H, it's delta. These are the ground states of this Hamiltonian, okay? They don't look like superfluids. So we described in these lectures the ground states under this Hamiltonian, and they look like superfluid states with phonons. Then I described the ground states of this Hamiltonian, and they look like two particle states in ADS. There is no superfluid. How do you go between them? You can do this and try to ask what are the ground states as a function of mu. And people are trying. There might be regimes where you get particles or that then collapse to a superfluid. There might be a complicated phase diagram. So there is no superfluid in this story. The superfluid appears here. But these are both limits where you can essentially solve the problem.
But we can't think of this ADS thing as some effective field theory for not J in the same sense we did.
Yeah, so the question is, can we regard it as effective field theory? The answer is yes. So it appears that the correct effective field theory for this problem was a superfluid with phonons. The correct effective field theory for this problem is almost free particles in ADS that are spinning far away from the cosmological scale L. So it seems that, like, yeah, you just get a weird effective field theory in ADS D+1. And you can do calculations in that effective field theory.
And what would be the cutoff for this effective field theory?
Okay, so the question is, what is the cutoff of this effective field theory? It's when J becomes that small enough that this 1/J corrections start competing with this. So I would say the cutoff is like around J equals 2, J equals 3. You'll have lectures, I think, in the last week by Simon Caron-Huo. And essentially what Simon did a few years ago is to show that you can extend these formulas as analytic functions of J. And the formalism works all the way to J equals 1. So that was the main thing that he did. He made J into a continuous. J here was a discrete integer. Simon promoted J to a continuous parameter, and he interpreted it as an analytic function. And he showed that these analytic functions make sense and satisfy some nice dispersion relations all the way to small j. I think that's what he's going to explain the last week.
It's next week, actually.
Next week. So this is a good preparation for what he's going to do. So this formalism works all the way to small j. And these particle states exist all the way to some very small j, according to Simon's formula. In this description, it seems like it's an expansion. Maybe it works up to j equals 10. But he actually showed that you can make sense of it all the way to small-ish j. Yeah. Right. So. Yeah. So the question is, how do we know that this is the ground state? So if you consider 3 particles or 4 particles spinning in some funny way, you'll get a contribution from each of the partons. If you just have 1 particle, it's not a primary, because I showed that 1 particle is a descendant. So it makes a lot of sense to assume that the smallest possible primary is made out of 2 partons. If you add 3 partons, you're just going to increase this piece. You'll get a sum over deltas. You'll get a sum over deltas plus j. So the way to decrease the dimension as much as possible is to have 2 partons. But sometimes you have no choice. People have found situations where you need many partons to minimize the energy. That's when there is some constraint on the number of partons. Like maybe if you study this Hamiltonian, you have to have mu partons. Then you cannot really have 2 partons. That's not the ground state. But that's more complicated. That's okay. Yeah.
I want to know if in conformal field theory we can consider some maybe for double trace we can have 2m plus j. This is ground state. This is the same counting with the ground state in ADS. Is that right?
Sorry, can you repeat the question? I didn't.
We can construct the double trace operator, right? You're using
Yes.
partial square
Yes,
and
yes, yes.
Partial j, and this corresponds to the ground.
It's not called double trace. It's called double twist. Double trace is a notation from large N holographic theory.
Yeah, if I have more operator, and we can also construct primaries.
Yes.
And that counting is related to the number of these ground states in AES.
You can construct primaries made out of 3 particles, 4 particles, Q particles. They are not the true ground state of delta minus j, but it doesn't matter. There are still interesting primaries in the theory, and we know their scaling dimension with great precision. So if you look at the notes that I put on Slack, here I just plotted 1 curve. This is 1 family. But actually, people measured many other families, like this. And there are more families here. So we see that there is a proliferation of these objects that are made out of partons. What is it similar to? In QCD, we have protons, we have these mesons, those baryons. You can make many things out of partons. Even there are tetraquarks, yeah? So it's similar here. You can make many, many, many states out of partons. And like finding the true ground state maybe is not the most interesting question. The most interesting question is to understand which tetraquarks exist, so to speak. Which states actually exist as primaries, honest to God primaries in the CFT. So it's like a zoology of partons. And sometimes you get molecules even, very similar to partons in QCD, that you might have thought that you made a tetraquark, but it was a molecule of 2 mesons. So you get some things like that also. Yeah.
Gravitational potential in the boundary? Like that, sorry, the Newtonian potential?
The gravitational, so the question is, what do we do with the gravitational potential on the boundary? There is no holography here. ADS is just a machine to compute these scaling dimensions. So the gravitational potential is something that exists in ADS. It allows us to compute these corrections to the scaling dimensions of primaries, and then we go to the Ising model, and it works. So we see the gravitational potential in the Ising model. There is no gravity in the Ising model. But the calculation of the gravitational potential in ADS4 happens to give you the exact answer here. That's it. So it's like that's why I said that it's like ADS-CFT, but there is no ADS-CFT. It's an effective, it's just somehow in this, here you can think about the Ising model as a theory in ADS4 with gravity and maybe some other interactions. But yeah, okay.
I guess what you're asking is like if I was just in CFT and I saw that deviation from the
Yes.
what's kind of like the leading effect that I would think?
Okay, so you can say I don't want to hear about ADS or gravity. You can ask how would I understand this in the CFT? So the answer to that question is very well understood. You can get these effects in calculations in the CFT without ever saying the word gravity, using the bootstrap equations on the light cone. Maybe there will be some lectures here about it, I'm not sure. Maybe Simon will explain it. But you can write the bootstrap equations of the conformal filter on the light cone, and they become very simple algebraic equations. And one of the terms that appears is the operator product expansion of 2 sigma fields into the energy momentum tensor. And that piece of the computation happens to be just mathematically the same as calculating the gravitational potential in ADS4. So there is a CFT way of getting it without ever saying the word gravity. Yeah.
Higher dimensional CFT, we only consider this scaling dimension OP coefficients. Thus is not meaningful in the experiments, or if it is, then do we also compute that using the ADS?
Are you asking if we can compute OP coefficients for high spin operators?
For higher dimensional CFT.
Yeah. Okay. So yeah. So the question is, I only concentrated on scaling dimensions. The question is about OP coefficients, whether you can compute them at large Q or large J, maybe. Yeah.
Maybe before that, is it like meaningful experimental?
Oh, you're asking if it. So there are 2 questions. One, can we compute them using effective field theory? Then the answer to that is yes. There are many papers that computed OP coefficients for heavy charge Q operators, this phi to the Q. We have exact results for their OP coefficients. And there are many papers about OP coefficients of these highly spinning operators too. So the answer is that we can predict it. Is it easily obtained in Monte Carlo? No. Is it known from the bootstrap? I don't know. I actually don't know if people have tried to match it. I don't know. Huh? Okay, so he says yes, that that people tried, yeah.
So in ADS, you can compute this by computing some amplitude.
In ADS, it would be like computing. Yes, in ADS, it would be like computing a scattering amplitude between states like that, highly spinning states.
But in CFT, it's like only via Monte Carlo.
In CFT, Monte Carlo?
I know Bootstrap does.
Bootstrap. He says the Bootstrap people have computed it. And it works?
Yes.
Yes, it works.
If it is experimentally meaningful or not?
Experimentally meaningful, what is meaningful is anything that's observable is meaningful. So yes, it's experimentally meaningful, but it's difficult to extract an experiment. Because in experiment, 2-point functions are easy to measure. You read off their exponential decay, and you match to scaling dimensions. But 3-point functions are difficult to measure. So it's meaningful, but maybe not measured, I don't know. Okay, yeah.
Can you be more intuitive about why you say ADS-CFT is contactless, like in supervising scales? Is there like a way? Is there a way to like understand it in terms of like, symmetries of ADS you would apply to some horizon scales? Is that kind of
I wasn't saying, I was saying that ADS CFT has content only when the physics in ADS is valid on sub-horizon scales. If it's a non-local theory in the bulk, it's just contentless. And so I'm not saying that we have a holographic correspondence here. I'm just saying that for large rotation, the physics in ADS is local because the non-locality is on the horizon scale, on the cosmological scale. So the physics between this, the physics that controls these highly spinning states is local, and we can use it to compute. But it's not that there is a holographic description of the Ising model. In other words, we have a good computation in the Ising model of this kind of piece of the spectrum using ADS, but we don't have a computation of this piece of the spectrum. So there is no full-fledged holographic duality, only some piece. Okay, thank you. So I'm done.